Okay, guys, so I think we can start. So now, in this session, we start with an invited talk by Tucker Taft. So he is Vice President of Language Research at Adacor, and he's going to talk us about sound and precise static analysis using a generalization of SSA, static single assignment, and value numbering. So Tucker, the floor is yours. Stay in about a slot of 40 minutes. Of course, if people have questions, we can, so everything seems to work, so we can interrupt him and ask questions live or at the end, okay? The floor is yours.
Sounds good. I thought I would try to have the longest title of anyone in the presentation, so I think I may have come close. I'm sorry I'm not there in person. I got up at 5 a.m. this morning, and just before I got into my Uber, I checked my email, and Delta Airlines informed me that they had canceled my flight to Florida, so that was a little disappointing. I came back from Portugal yesterday just so I could fly this morning, so it was a little disappointing, I have to say. Figured interpretation system because, as we know, there are a huge number of different sorts of domains and different techniques and so on to make abstract interpretation as precise as possible. The nice thing about an SSA-oriented approach is it's actually a very straightforward set of computations that you're doing, and they don't need a lot of special casing and so on. And there's also a category of tools that that would basically, they don't care whether they're under approximating, over approximating. Their goal is to try to find bugs and not have too many false positives. There is an interesting tool that I have just recently come to know a fair amount about, is the pulse mode of the infer tool that comes out of Facebook. And they systematically under approximate. And my little high integrity warning bells go off and say, why under approximate? And they basically want to have zero false positives. And so it's interesting, if you flip the whole equation around and say you actually want to have zero false positives, then you have to be sure that every outcome you consider is one that you know will in fact occur. And so that's really the principle behind infer. So it's an interesting approach. It's obviously quite different, but it is, it serves its purpose. So just a quick example of soundness and precision. Here's an example of some code that's written in a sort of a variant of Ada. And I'm asserting in the beginning that x is in the range 1 to 10. And then I multiply x by 2, add 1, and store it into y. And then for some unknown reason, if x is in the range 2 to 5, then I'm going to subtract 5 from y. Otherwise, I'm going to add 5 to y. And, I can't think of any reason you want to do this, but the static analysis tool doesn't wonder why. It just goes ahead and tries to figure out what the possible values of all the various variables in this picture are. And x is pretty easy. It's in the range 1 to 10. When we go into those then parts, we know it's either in the range 2 to 5 or in the range 1 or 6 to 10. And then once we know those possible range values for x, we can go back and see, well, y is 2 times x plus 1. So we therefore know the range of y. And then if we subtract 5, we can come up with a range. And if you are sound, then you want to over approximate. So you don't want to miss any possible values for y. And so a sound over approximation of y would be minus 2 dot dot 16 in the then part and 8 dot dot 26 in the else part. And if you want to get precise about it, you can say y is in the range 0 to 6 and y percent 2 equals 0 in the then part, and y is in the range 8 or 18 to 26, and y percent 2 or y mod 2 is 0 in the else part. And then when you come to the join, you have to union them if you're doing over approximation. Under approximation, you can sort of do whatever you want. You may even intersect them because then you sort of know it's going to be hit one of these values. And then there's an exact value set, which, so again, this is just illustrating how there's soundness and there's precision, and to achieve full precision is not always easy or maybe even possible. And in fact, in this little diagram, I was trying to make the point that if you wanted to get perfectly precise static analysis every time, then you probably will have solved the halting problem. And that would be very interesting as well, but I'm not expecting that to happen in the next, maybe the next quantum computer will also figure out how to solve the halting problem. Okay, so a quick overview of abstract interpretation, which I suspect is not of interest to the people in the audience. But in my sort of high-level view, abstract interpretation tries to approximate the set of possible states in various domains of all variables at each point in the program. And once you've done that, once you've sort of got a sense of what are the properties of all of these variables, then you can use those properties to perhaps prove things about safety or security or correctness and so on. Typically, there's an iteration step where you iterate until a fixed point. Particularly if there are loops involved, you may iterate some number of times, then you may use some widening operator to kind of get the thing to stabilize. And one thing interesting about abstract interpretation, and also about the tool that we're going to talk about today, is that it's sort of computing the set of possible values by performing various operations and widenings and so on. Whereas things like model checking is more exploring the state space. And so abstract interpretation can in fact handle very large state spaces. Widening is one of the ways they handle it. Whereas some of the more exploratory tools like model checking can run into real trouble with very large state spaces, and it may have to go into kind of a symbolic approach and so Another thing that's relevant for abstract interpretation is that they will try to keep track of certain kinds of relationships, typically linear relationships. And then once you have some number of linear relationships that you know, you can represent the possible overall state of the program in terms of the total state of all the variables, typically with some kind of polyhedron, or if there are only two, it'd be a polygon. So this is my quickie presentation on abstract interpretation. There are some challenges, and much of the research around static analysis is dealing with some of these challenges. Polyhedral representation is fundamentally limited. You're limited to generally linear relationships, and that's, you therefore can't capture certain kinds of relationships between variables. You may need multiple domains with trade-offs in complexity, performance, precision, and so on to get the kind of ultimate precision that you want, along with having some reasonable time to compute. And may have to drop into kind of symbolic computations if you have inputs that are unknown and so on. Finally, there is the whole issue of scalability. If you take kind of the traditional approach where you start at the main routine and you sort of followed from the starting point of the program down to lower levels, you can have serious scalability problems unless you can somehow reuse what you've learned when you encounter the same procedure multiple times. So there are a lot of tricks, there's a lot of technology, there's a lot of research. So first, quick refresher on SSA. I don't think many of you need it, but I'm going to quickly go through a little bit. So the static single assignment, if we have a procedure here written in sort of a variant of Ada, and we've got variables like result, whose value is changing and being assigned in multiple places. Similarly, we've got count, whose value is changing, and so on. This makes analysis a little bit harder. The first step is typically to create a control flow graph where they are made out of basic blocks, where a basic block is a sequence of code with no internal control flow, and the entry, a single point of entry, single point of exit, which is typically or often a conditional of some sort. So you might be checking the value of y and then going one way or the other. So this is just a transformation of that program into a flow graph. And then we can also, so I can label the program with the flow graph. But the point I was making earlier is that these def use change, that is the chain from where something is defined to where it's used, can be a little complicated. For example, this execution, the first time through, it's coming from here. The next time through, it's coming from itself. And this return here may be coming from there, maybe coming from there, maybe coming from there. So with static single assignment, one of the things you do is you transform this and you create new variables effectively, and we typically use subscripts in the first step. So you've got results of 1, results of 2, results of 3, results of 4, and results of 5, and each of them is assigned exactly once. That's the static single assignment aspect. Similarly, of counts of 1, counts of 2, counts of 3, and one of the important operators that is introduced to achieve static single assignment is this so-called phi operator, and it's also called apparently the phi comes from phony. I never knew that until I did a little research recently, but phi is short for phony. It's a kind of a phony function. It takes the two different versions of result that might be live at this point and combines them. And it basically says, well, if you came from here, then you're going to be the value of result 1. If you came from over here, it'd be the value of result 4. So these are basically the number of different ways you can get to this point, and each one has its own value for result. Same thing with count, and so on. And then you can transform the control flow graph. Now your def use chains are simpler because these things are unique. You reference result 1, you know it came from here. If you reference the result 4, you know it came from here, and so on. So, okay, that's my big SSA overview. So what's SSA-based static analysis? And this is a technique that, I don't know if you recognize the name Robert Morgan, but he wrote a fairly well-regarded book about compiler optimization. And I, in fact, worked with him back in 1982. And one of the things we implemented was a version of what I'm describing now. And the basic trick was you do static single assignment, and then you do what's called value numbering. With value numbering, we give a unique number, not only to every variable, but also to every expression. So every distinct expression is given a value number. And we go across basic blocks, and so it's called global value numbering. There's also local value numbering, which is just within a single basic block. I think the term global here, for most people, would probably mean across procedures, but in fact, the term global value numbering is referring to being across basic blocks. Every one of these value numbers that's assigned to a computation can be thought of as actually a combination of other value numbers. So, or it could be a literal value. We assign a value number to literals just for uniformity, and we assign value numbers to inputs. So if you have a parameter, you don't know what its value is, but you'll give it a number. You'll give it a value number. And then we can talk about it just like any other value number as being the value that this parameter had on input. So for example, here we're imagining we have value number 1 represents some input, value number 2 represents some literal, and value number 3 represents the sum of value number 1 and value number 2. One of the important properties of value numbers is that if we see the same sum, that is, the left and right operand are the same value numbers as before, then we produce the same value number as the result. They may be called different things by then. If you assign x into y, then you change the value of x, but you use y in the same way you use x, and so on. The value number might be the same when you do a sum, and we discover that you're doing the same computation that you did before we give it the same value number. So another interesting thing about value numbers is that they don't change. Even though the variable that they were initially associated with might be reassigned, the value number represents the value when it was defined and not when it might have been replaced as the current value of some variable. So variables take on different value numbers as they go through their lifetime. The value numbers have only one value, and they hold on to that value for their entire existence, if you will. Nice thing about that is they're now equational. So I can say, well, if vn3 is equal to vn1 plus vn2, well, that means that vn1, whatever its value is, it must be equal to vn3 minus vn2, and so on. So whichever one of these we know the most about, maybe we know a lot about vn1, but not so much about vn2 and really nothing about vn3. Well, then we can combine what we know into vn3. Or alternatively, we might know more about vn3 than we do vn1, and we can propagate the other direction. So the nice thing about value numbers is that you can propagate information forward, backward, up, down, depending on how you look at the world. And the other key thing is that, as I mentioned, for abstract interpretation, you're trying to compute something about each of these variables. And the most precise thing you can do is what are the possible values this variable could have? And I'm just going to call them value sets in this description here. And so in this approach to static analysis, the key thing is we associate value sets with value numbers rather than with variables. So that's probably the fundamental difference between what we're doing and what typical abstract interpretation is doing. That means that once we value numbered a program, we can now throw away the program and just look at the value numbers and do all of our work on value numbers and the value sets associated with them. Another interesting thing you can do with value numbers, and I'll get to this in more detail, is that pre and post conditions can actually be inferred from the final value set that certain value numbers have. If you have a value number that represents an unknown input, and then you press it through a program, and at points that the set of possible values shrinks every time you use that value number. If you use it as an index-owned array, well, if you don't want it to fail, then the value set will shrink down to being a value that can legally be used or safely be used as an index into that array. Similarly, if you use it as a pointer, you want to know it's not null. Essentially, every use of a value number may impose additional constraints on it. And if the value number's value set, whatever makes it down to the exit block, those are good values. Those are ones that actually could survive the checks. And anything that's not in that final value set, those are bad values, because those are almost certainly going to trigger some kind of a runtime failure. And so if we can say this value number must be within this value set to make it to the end, you can turn that around and say, well, that's actually a precondition. If that value number represents the value of some input, then we've now got a precondition that input had better be within this value set to not create problems during execution. So let's go to the next slide. There we go. So what makes this kind of analysis more precise? Well, I already said that value numbers don't change in value over time. But what we know about them does, because when you use them in some sort of checked construct, we shrink them. If you use an if statement, the value number of the thing that you're testing, in the then part you know it's true, in the else part you know it's false. One of the things that we do as part of our process of sort of parsing the program is we convert all comparisons like y times 2 greater than x into a membership statement. We're saying y times 2 minus x is greater than 0. So we've converted what was a comparison into a statement about the value set of a subtraction. And similarly, in the else part, we've done effectively the same thing, but now it's a different set of values. The interesting thing about doing this canonicalization is it makes it very easy to combine pieces of information. In one case, we say, if x is greater than 5, then do this. If x is less than 3, then do that. Each of those have turned into a statement about the value set of x, and you can union them, intersect them, and so on, much more easily than comparisons, which are kind of awkward to combine in various ways. And as I said, value sets also shrink when you do assertions. So if we assert x plus y is greater than z, then we've effectively asserted that x plus y minus z is in this range. One of the nice things is that overall the value sets shrink. You start off with knowing very little, and then as you move down the program, the value sets shrink, which has a nice, essentially ensuring some kind of convergence. Another nice thing about value numbers is they can capture arbitrary computations. Typically, when you start doing relational domains in abstract interpretation, you have some limitations on the kinds of relationships you can represent. A value number can represent anything. It can represent any kind of computation. And any kind of a comparison can be turned into a subtraction, which then we can learn something about. So these two slides, I will say, is the heart of SSA-based static analysis. And so if you don't understand these two slides, now would be a good time to ask a question. Are there any questions out there? I can see things written in the Discord channel, or you can speak up.
Yes, there is a question.
Boy, I can't hear that, though, unfortunately.
Can you hear this?
Can you say that again?
Can you hear me?
Yes.
Okay. In terms of implementation, how is the vset itself implemented?
Excellent question, and I'm coming to that. So,
okay, sure.
The vset is represented. I mean, you could represent it as sort of approximately as you want. You could have a low bound and a high bound. You could have a sequence of ranges. You could have a combination of range and some modular, congruence information, like we know it's even, we know it's, it can be arbitrarily complex. It turns out that for our tool, we represent it as a set of ranges. So it's precise in as much as we can do that. If the number of ranges gets too large, we may combine them because we want to over approximate. But we try to have it precise. So we know when things are not equal to 0. We know when they're, greater than 10. We have a very precise range. Other questions?
No.
Okay, great. Okay. So how is the overall analyzer structured? The first stage, first we have a representation of the program we call statically checkable intermediate language. And then we have an aliasing phase which analyzes the various objects and generates aliasing information, which is then used by the static single assignment and global value numbering phase. And the net effect of that is to create value numbers, which capture the distinct possible values. Aliasing is important because if you have arrays and elements of arrays, if you assign into A sub j one value number and assign into A sub k a different value number, the question is, what is the value number of A sub I? It may have to be some kind of combination. So we create new operators to represent that sort of ambiguity. We also have more recently implemented a whole new approach for doing variables that are aliased with one another. And if I have time, I'll talk about it, but I sort of doubt I'll get there. But anyway, and then the final phase is what we call the possible value propagation phase. So we're not just propagating known values, we're propagating possible value sets. So these value sets are propagated around the tree, and they allow us to, and then we go through a iterative process. And by the time we're done iterating at a fixed point, we now have a value set for every computation and every reference to a variable for that particular location. And we generate annotations and warnings. Warnings are where we see a place where the value set is potentially going to fail at runtime because perhaps it's 0 and you're doing a divide, or perhaps it's too big and you're using it as index. And we also generate annotations, which essentially capture information about the procedure. And these are used not only for as-built documentation for humans, but they also act as summaries. This entire process is bottom-up, so it's very scalable. And we can do all of the computation on a given procedure and then propagate to all the callers what we've learned. Okay. So I'm going to focus just first on this middle phase, this static single assignment global value numbering phase. So global value numbering, we talked about what static single assignment is. To figure out what value number to assign, we give each variable in the program, so x, y, blah, 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 its own value stack. And on that value stack, we're going to put value numbers that get assigned to it. And each fetch of a variable simply fetches the VN from the top of its value stack. So you can imagine you have these value stacks for all the different variables. And then as we go through the program, value numbers appear on this stack. And then as you pop back, so for example, we go into an if statement, we might put a new value on x, then we get to the else, we pop it off, and we put on a new value for the else part, and so on. And I'm going to step through this quickly to show you the kinds of things. So the first assignment is putting a value number 1 into y, and we have a table that keeps track of what do these value numbers represent. Value number 1 represents the literal 42. Then we have the assignment, we have the reference to x. X is an input. So the initial value number for x is going to be v2, and it is sort of the initial value operator. And I've just denoted it this way, but effectively it's whatever value x had coming in. And then what's the value number of z? Well, it's this v3, which is a computation of plus of v2 and v1. So now we have a value number representing not only the current value of z, but also this computation of v1 plus v2. And if we ever see that again, we'll give it v3 again. And then we now have a computation of v4, which is checking to see whether v2, which is our current value of x, how it relates to minus 5. And so it's saying, is v2 in the range minus infinity to minus 5? If it is, then we go to the next branch and we push a new value on v3. So we're pushing values here instead of just overwriting. That allows us to pop them when we go to the else part. So we put v3 on x, which we computed up here. And then we go to the else part, we pop it back off. We go to in the else part, we then do a new computation, which is v5, dividing v3 by v2. And we then assign that into x, so that's the current value of x. And then we pop it off. And finally, we want to know, what's the final value of x? It's one of these phony functions. And its inputs are whatever the value was coming in from the then part, and whatever the value was coming in from the else part. We typically do this in 2 passes, where we first sort of walk through once, and then we come back and we fill in all the fees that we find we need. We don't necessarily know in advance which fees we will need, so we can do this in 2 passes. So in the second pass, we discovered that the value coming in from the then part was v3, and from the else part was v5. So this is the final value number table. Okay, so that was a fair amount of work. So why did we do it? It was so that we could predict possible values at every fetch of a variable and every computation of an expression. We have given these things unique value numbers. So now we need to, once we can figure out the possible values, we can determine whether the use of the variable or expression might cause a runtime failure. Since value numbers are stable unlike variables, we can combine information that we learn about them in different places. So if the same value number appears in two different if statements or two different assertions and so on, even if they're from different variables, if they're referencing or affecting the same value number or applying to the same value number, then we can combine that information. The sound analysis means that we never intersect these things. Generally, we are combining them in sound ways. And we strive for precise analysis. So as I mentioned, our value sets can be multiple ranges. So we can easily represent things like not equal to 0. And we could also represent congruences like x mod 2 equals 1. We have not chosen to do that because it doesn't come up that often. More often, it's the low and high bound you care about, or is it equal to 0, and so on. But if you found that that was a serious issue, then you could certainly add that. And then the thing I mentioned about pre and post conditions was, if you have a VM that represents an input, like x, the final value set for that represents the value, the final value set for the initial value number. So those are two sort of different things. Represents a precondition, and the final value set for an output, the value number corresponding to an output, is essentially a postcondition. So here's just a quick example of how we decorate the tree with value sets for each value number. And in fact, we have a separate value number for each basic block. I'm sorry, we have a separate value set for each basic block. So I'll quickly go through the possible value set propagation. We have one of these tables for each basic block in the flow graph. And it says the value number 1 is in this range, value number 4 is not a null, value number 7 is in this range, value number 9 is pointing either to object 2 or object 4. So we deal with pointers, integers, we also deal with floats, and so on. And when one of the value numbers sets shrink, that may also affect other value numbers. Because if, remember, we had, for example, v3 equals v1 plus v2. If what we know about v1 improves, then that also may allow us to know more about v3. So when we shrink one value set, we propagate it across the interconnected network, if you will, of value numbers. And then once we've got all of that stabilized, then we can actually, in our final pass, we will check for runtime failures and assertion failures and precondition failures on calls and so on. I think I'm going to jump ahead here. So I mentioned how preconditions can be inferred, and this is a concrete example. And the same thing applies to postconditions. And this is just an example of what kinds of pre and post conditions we can infer. So here's a little program that's popping something from a stack, and if we look at how these, like a global variable last is used, it's used as an index into this array, we know it must be in the range 1 to 200. It turns out that one of these functions references the E component of variable V, and so we therefore know that that needs to be initialized. And when we get this value off of the top element of the stack, we then dereference that value, so we know that that has to be not equal to null. And as post conditions, we now know that last is last tick old plus minus 1. We've subtracted 1 from it. We know it's now less than or equal to 199 because it came in 1 to 200. And we know that the value of the result is going to be one of the elements of the table, and it won't be null. So I'm getting low on time here. Have you got how many more minutes have I got? 0?
Let's say about 10.
Oh, 10. Oh, great. Okay. I thought you were cutting me off early. Okay, good. Well, then I'll go a little further. So I showed you how we dealt with assigning value numbers when we had simple variables, x, y, z, and so on. But if you've got array elements, you have to worry about aliasing. So if you assign to one of them, then, for example, here, we assign minus 5 to j, a sub j. So we have a separate value stack for j, well, then we put minus 5 into it. But then if we assign 42 into a sub 2, well, what's the value now of a sub j? Well, we know that a sub 2 is now 42, but a sub j is now, if j equals 2, it's also 42. Otherwise, it's minus 5. So this is a little bit of a conditional expression for the value of a sub j after doing this assignment to a sub 2. So this is how one way you can deal with aliasing if you're doing value numbering is you associate different value numbers with each element of an array in each sort of way you refer to an array. And you have to worry about aliasing. You have to create these conditional expressions. We call them kappas for partial kill, if you will. And then you have these extra value numbers. The whole thing gets pretty messy. And I'm not going to force you to go through it because it is so messy. You have may aliasing, you have must aliasing, and it all gets sort of nasty. So one of the things that we did a few years ago was we created what we call aliasing groups. And rather than trying to keep separate track of individual elements of the array, which is sort of a losing proposition because ultimately you know relatively little about any of them. Instead, we've created what we call a value history, which is essentially a big, think of it as a big wide value number that represents the state of a whole array. This notion of array static single assignment originated, I believe, in a paper by Kath Nobe and Sarkar, forgetting his first name, back in '98. So it's not a new idea. I think the thing that we've done is we have linked it into the whole concept of value numbering, because for us, value numbering is actually what gives us the real power, our ability to do very precise static analysis. So now, in the newest version of our tool, we don't have separate value numbers for each array element. We don't have separate value numbers for each pointer, dereference, and so on. We group all potential aliases under a single conceptual stack element, if you will, and that element now has operators that are more array operations, such as there'd be an empty value number, which is a totally uninitialized group, an extern value, value history, which would represent an array coming from the outside world, a disjoint assignment value history, which is a set of assignments that you know don't overlap with each other. So they could be done in any order, and they represent the state after those assignments are done. And then a phi value history, which represents when you start joining different value histories together. And so it's very analogous to the way we do value numbering, and it's allowed us to eliminate a lot of the complexity and, frankly, a little bit of the unsoundness associated with some of our attempts to assign value numbers to individual array elements. And this is how it would look, the same program, if you were to use value histories instead of value numbers. So we still use value numbers for simple variables like k. It's about the only simple thing in here that's actually changing. And then we use value histories for arrays and things like that. And here, the only element we really care about is array. And this shows us what are the different value histories that represent the overall value of the array A. And value histories are nice because there are many fewer value stacks to worry about. The overall effective routine can be captured by a single value history stack. And the pattern of assignments to an element of an array is represented by the value history graph, if you will. And that's allowed us to recognize certain common patterns of assignments, like assigning every element of an array, either forward or backward, or copying one array into another, and so on. And those are now recognizable just from the value histories that we've accumulated. Okay, so I want to now jump into some quickie examples of how this all works out. So here's a program that is just summing all the elements of an array. The individual elements are in the range 0 to 100. The sum is limited to the bound of an integer, let's say 2 to the 31st minus 1. And if we just run this program, if this array is big enough and the values are large enough, then we might get an overflow right here on this line. Depending on the length of A and the average value of the elements in the A, this could overflow even a 32-bit integer. So sure enough, if we run this through our tool and we have not specified any kind of a precondition on the length of A, we get the following. It infers a precondition that either the length is 0 or A sub I had better initialized. So it knows that you're referring to the content of A, but only if the length is greater than 0. And we know that the sum itself is going to be greater than 0 because of the sum of numbers that are greater than or equal to 0. So these two things are inferred from the code. And here it complains. It gives it a low ranking, which means that we're not totally positive you're interested in this complaint, but anyway, here it is. This computation here requires that the result plus a sub I is less than or equal to integer 32 to class. If it's greater than that, then you'll have a numeric overflow and the program will raise an exception. So can we fix this? Well, Ada has pre and post conditions, and we can say, well, we're never going to give it an array that's more than 1 million elements. So let's make that explicit. And if we go to the next thing, we will see by adding this precondition onto the declaration of the function, we now get 2 preconditions. One which comes from the user. It just says atig length. It better be less than or equal to 1 million. So that's just essentially echoing what the user wrote. This one is the same. And then here we now have a post condition that's more interesting. It says that the value of result is in the range 0, ... 100 million. And it was smart enough to be able to compute that because each individual element is in the range 0 to 100. There might be 1 million of them here. And so 100 million is the maximum possible value of the result. So this is all done with value numbering and incorporating user-specified preconditions and inferring other preconditions and post-conditions. Another example is transitivity. I think it's a little bit too complicated to go through right now, but one of the things that is interesting is that computers don't automatically know transitivity. A is less than or equal to B and B is less than or equal to C. Well, then, of course, A is less than or equal to C. Of course is not one of those operators that at least my static analysis tool has. So we had to actually help it. And we recognize cases when you have this kind of a triad, as we call it, where you have A minus B, B minus C, and you now want to know what's A minus C. Well, it turns out that if you know A minus B and B minus C, then if you add those two things, if you add their potential value sets, you get the value set for A minus C. Is this useful? We have about 1,000 tests that we run every night, and 30 of them showed new false positives when we turned off this thing. And it's possible to incorporate this into abstract interpreters. In fact, some of it sort of falls out if you do relational domains, so long as those relational domains are symbolic. Here's an example of how you would do it in an abstract interpreter. You'd essentially create a polyhedron, which is this little triangle, which has the right property that A is less than or equal to S to glass, which is sort of the important one. And in SSA based, in value numbering based, we do it with triads. We recognize these triads of 3 value numbers that represent this is sort of A minus B, B minus C, and A minus C. We recognize that. We therefore then know that we have this this rule that these if you know something about this value number and this one, then you'll know that one, and so on. And it goes both ways. Okay, I'm going to wrap this up now, and let's see what we got. Okay, so I think an SSA-based approach, and as I said, value numbering is definitely an important part of that. It tracks value sets of value numbers each representing immutable values, as opposed to tracking mutable variables using multiple domains. You can incorporate things like user-specified preconditions. We also do precise loop induction variables and so on. And we can infer preconditions. We can use transitivity. There are a number of things we can do that are quite precise. And sort of the bottom line is that we get a very unified, precise, and sound analysis. Thank you for your patience.
Okay, thank you very much. So, any question? So I have a question about what's the complexity and the slowdown induced by using SSA when you are performing analysis, because at least in my experience, when adding more and more variables like what SSA does, often relational domains in particular, they slow down quite a lot. But I don't know if this is true, like in, let's say, more real-world examples.
Yeah, we certainly do analyze programs in the million-line range. We go at about 100,000 lines an hour, so it's an overnight process to analyze 1 million lines. We do hope to make it faster. We continue to do that. It's not as bad as relational domains because they tend to have some kind of a exponential effect, where if you have 10 variables that you're trying to worry about all the relations between them, then you have to worry about 2 to the 10th or various big numbers. Here, we're only really creating value numbers for expressions that appear in the program. Now, they can be arbitrarily complex, but they're things that the programmer was interested in. And we also create them implicitly for certain kinds of checks. So if there's a check that this index value is less than array tick last, well, that becomes also something that is assigned a value number. So we don't assign value numbers for every possible combination. They are only the ones that are interesting to the user. And we only compare them when they show up in checks of one sort or another. So we aren't sort of propagating useless information. These are really things that are interesting and do control whether a given check will or will not fail.
Okay, we have also a question from Eneza Fanella online. So he's asking, am I correct if I say that SSAVN analysis, when not using some enhancement like the one for the transitivity, can derive a relational constraint on two variables x and y only when they occur together in an expression?
Yes, you do. I mean, well, actually, there are other. You can learn things indirectly, if you will, but if you really want to get precise transfer of information through transitivity, you have to add this recognition. We have a small number of, essentially, there are certain kinds of algebraic equivalences that we incorporate into the analysis. But there are definitely indirect effects that are propagated through this overall. You change something, it is used to implement, maybe it's an element of a sum, and it's also an element of a subtraction that will indirectly have influence on the other two value numbers. So you get some indirect connections, but if you want a direct connection like transitivity, you do need to include equivalences.
Okay, yeah. There's another question here.
Thank you again for the nice talk. I have a question whether this SSA-based approach would also work for concurrent programs that somehow communicate with shared memory?
Yes, I mean, we do concurrency checking, although a lot of it is about alias analysis. I mean, that's sort of where we start and worry about alias analysis. The actual issue of things that are kind of binary, do these things conflict or not, are very simple from an analysis point of view compared with what is the range of values of a given value number. So if you just know it's either true or false, or they conflict or they don't conflict and so on, that becomes an easier problem, although aliasing now becomes a much bigger part of the equation, because that's where you worry about, is this task referencing a piece of memory that is also being referenced by some other task. So it's a somewhat different problem, and value numbers are not particularly challenged by that. I would say that it's more the alias analysis that has to play an important role.
Thanks.
Okay.
Yeah.
One last question.
Okay.
I'm curious how precise the alias analysis used here is, and then kind of a secondary question on that is if it's reasonably precise, is that part of the reason for or is that a significant chunk of the computation time?
We do two alias analyses. I showed you there was a whole phase called the ObjID phase that does a high-level aliasing, and it basically says, is it conceivable that these two names might refer to the same variable? And it's largely flow independent, largely context independent. We do propagate, everything we do is bottom up. So each procedure indicates what might be aliased, and then it passes up to its caller to worry about whether it really is aliased, because it might be between two parameters and so on. Ada actually says that you cannot have aliasing if the aliasing would affect the result of a computation inside the called routine. You can't have two parameters that might or might not be aliased. And so we in fact propagate up whether, if these two are aliased, that's a bug. So we actually propagate up aliasing checks. But that's where the precision comes in is when you start having things like array indices. And there we do another alias analysis in the final PVP phase, where it's now trying to know, could these two names refer to the same object? And here we have A sub j and A sub k. At that point, we know very precisely what the value set for j is and the value set for k is. And now we were told they might be aliases, but now we know if j and k do not overlap, if their value sets do not overlap, then we know they're not aliases. So we essentially do it one fairly high level, fairly fast, fairly flow independent, and so on. And then at the end, we do it absolutely as precise as we can. We use all the information we can to say, okay, here's the place where we're doing something. Are these two things aliased?
Okay, well, let's thank again the speaker.
I'm happy to answer questions if people want to send email. It's taft@adacore.com. Pretty simple.
Okay.
Thank you very much.